welcome to the course Advanced Reaction Engineering. So, we are discussing steady state non isothermal reactor designs. So, in our previous class we already have discussed multiple steady state for a reaction. So, when we operate a reactors and we conduct a reaction, so depending upon the feed inlet temperature, so there might be possibility the different steady state means maybe depending upon the feed inlet temperature one steady state possibility is there. If also feed inlet temperature is different, then 2 steady state, 3 steady state temperature might possibility is there. So, how that would impact in the reactions, so that we will discuss, and what should be that means when that means how we can avoid that means suppose non isothermal reactors we are operating. So, let us see runaway reactions in a CSTR and multiple reactions in a CSTR. Suppose we are conducting multiple reactions. So, in multiple reactions more than one reactions might possibilities there. So, that is conducting or taking place inside of the reactors when we conduct a reactions inside a CSTR reactors. So, in that reactor or reactions, so runaway reactions is there. So, how to avoid runaway conditions for a reactions or of a reactions when we conduct the reactions inside of a reactor. So, what is runaway conditions means that I said means in our previous class that when we conduct a reactions always we expect that reactions should operate under steady state conditions whatever the feed inlet temperature. So, let us say feed inlet temperature is fixed, but when we operating the reactor under steady state conditions. So, suddenly since the reactions multiple reactions will take place, multiple reactions is there. So, this type of reactions or maybe this type of reactions, this is the series reaction, this is parallel reaction. So, either if this is exothermic, this is endothermic reactions. So, then overall if it is exothermic reaction somehow heat generation should be more. So, means slight increase or decrease of the reaction temperature that would affect overall reaction. So, therefore, so once we design the systems or reactors, so then these heat removal lines, heat generation lines from the energy balance equation. So, we can develop this way means if our feed inlet temperature or TC temperature, that is the this feed inlet temperature. So, if we let us say operate these reactors or feeding the reactant in the reactors at this particular temperature. So, heat removal lines would be this. So, here 2 steady state point is there, but if it is possible to develop instead of A, B line is possible. So, means heat removal lines is B instead of A we have. So, then in this case you can see one steady state point is there, but in this case 2 steady state point is there. So, here one steady state point is there. So, by that way we can operate this reactor at this current temperatures. So, but if this temperature is sufficiently high, so then that is also not good for the reactions. Why it is not good for the reactions to operate the reactors at high temperature, since here we are getting one steady state point, but the steady state temperature is very high. Here we can operate this reactor at this temperature, this is also steady state temperature, this steady state temperature is low, but if somehow slight temperature increase is there, heat generation terms would be more. So, here instead of here you can see heat generations is more than heat removal at this particular point. So, slight increase in the temperatures. So, this steady state will be disturbed and the reaction or reactors will operate at this temperature. This is sufficiently also high, this is not expected or desirable. So, therefore, this runaway conditions is coming. So, this is the operation at steady state. If the reactor operate at this condition, it is fine, this is acceptable. But when heat removal terms or gradient of RT by dt less than dg by dt. So, this is called runaway conditions, means heat removal is less than heat generations. So, once it is happened inside of the reactor, so then many problems will appear. How we can avoid that, that basically we will discuss. Okay. So, means if we operate means sufficiently high temperatures or upper steady state and the temperature is sufficiently high, that has the impact on the reactions. So, how means that is undesirable or dangerous to operate at high reaction temperature. Why? When reaction temperature is very high, then there possibility is a secondary reactions, means side reactions or undesired reactions, undesired product formations is there at sufficiently high reaction temperature, that is not desirable for a reactions when we operate. So, always we expect the reaction should be operate at a temperature where undesirable reactions, side product formations are there less. Or second possibility is that evaporation of the reacting materials, that also possibility is there. Either side reactions, undesired product formations or evaporation of the reactant materials, these are the possibilities are there. So, therefore, how we can avoid the runaway conditions. So, this line is runaway conditions. So, this is very good, but here also the reaction steady state temperature is very high, and if we operate the reactions at these conditions, there is no, this is steady state, but ignition at this particular temperature, ignition temperature here, if we slide increase or increase in the reaction temperature, then it will reach to the this temperature. So, here's runaway or ignitions when you move from lower steady state to the upper steady state. So, these runaway conditions here will occurs, means ignitions or runaway that is occurs in between that. So, we are moving from lower steady state to the upper steady state temperature when just slight increase of the heat generations. Okay. So, this condition is very good, means at this particular T star, that is the temperature we are operating the reactor. If gradient, temperature gradient for tangency of heat removed to the heat generators both are equal, so this is acceptable. So, but somehow that would be change, decrease or increase. So, these are the terms how has come. So, that long derivations is there. So, we will discuss, this is the energy balance equation, this is the equation 1 that we have discussed. So, now x minus these terms means heat generation term is this and heat removal terms is this from the energy balance equation that already we have discussed, and this we can write x, we can write this way. Okay. These components we can write this way. Okay. So, means now kappa equals to u a by f a naught c p naught, and T c, that is the temperature, that is the T c, this is the feed inlet temperature, this is coolant inlet temperature or ambient temperature, and kappa, what is kappa, that is we know. So, T c basically dependent on T 0, that is the feed inlet temperature. So, now from here, so if R T and G T we have, if we differentiate with respect to the temperatures, so from equation, these equations we can write this, and these equations we can write this. So, differential form of dRT by dt equals to this and dGT by dt equals to this. Okay. So, this we can write this, and so we know this minus RA, that is the rate of the reactions, some constant Arrhenius equation or Arrhenius expressions means pre exponential factors exponential minus E by RT and some concentrations. So, that maybe Ca, Cb, what are the reactants we have taken. So, based on that rate equations we can derive that rate, we can substitute here. So, why we are substituting here rate equations, rate constant as a function of temperature. So, it would be here. So, then we can differentiate this, and after simply it means if we differentiate this component part. So, after differentiations we can get this. If we substitute it here, so basically we are substituting this. Okay. So, heat generation terms will get this equation 3 dg T star by dt, that is equals to this. So, these terms we can write A star, okay, or A star equals to this basically, okay, and heat removal terms is this. So, this is the gradient heat removal, this is the gradient for heat generations. So, here's or since heat removal and heat generation both are same when there is no runaway. So, at steady state conditions. So, equation 4 also we can write from the energy balance equations or that way. Okay. So, here A stars equals to this, or this is the equations. So, these equations we can write here G T equals to this already have discussed, and this is also energy balance equation, your equation 1 that we know that at the beginnings we have discussed or we have developed these equations from these equations basically. Okay. So, this is the equation 1, that is the energy balance equations. So, here you can see equation 5, from here equation 5 has come. So, that is basically has come from after this, if we substitute. So, you will get 4, and once we get equation 4 we can substitute, means here this GT part equals to this basically, that basically we are substituting here. Okay. GT part, rest this part remain as it is, and right hand side part is this. So, now equation 5 we have, equation 1 we have. So, from equation 1 and equation 5, if we divide equation 5 by equation 1 for 0 order reactions, these reactions for this here 0 order we are considering. So, here if we divide equation 5 with equation 1, so then you can see this part and this part we can eliminate, or we can substitute also. Then T star minus T c, that we can take as a left hand side, and right hand side rest of the components would be there. So, that is R T star square by E, that is equals to, and this basically here T star minus T, that is the T star minus T c, that is equals to delta T R c, that is the critical temperature difference. Means here T star, what is T star? T star is the temperature at which reactions we are conducting, reactor temperature at which the reactions will taking place, and T c, that is the feed inlet temperature T c. This is basically feed inlet temperature. If we change the feed inlet temperature, T c will change. Okay. So, one way you can say this is that feed inlet temperature also one way. So, this difference is the critical temperature difference, means reactor operating temperature and feed inlet temperatures. Means let us say we have a reactor operating at these temperatures, and T0, here we can see it is T0 or Tc. T0 is the feed temperature. So, here this is reactor temperature. If we enter the feed at 25 degree centigrade, and here the reactions operating at, let us say 500 degree centigrade, there is much difference 25 to 500 degree centigrade. So, this is actually critical temperature difference. If feed inlet temperature is 25 degree centigrade and T star, that is equals to 50 degree centigrade. So, here the difference and here the difference is huge, here 475, here 25 degree centigrade. Okay. So, this is the called critical temperature difference. If inlet temperature and reaction temperature, so the difference is huge, the difference between the reactor temperature and Tc is exceeded, the transitions of the upper steady state will occur. Okay. So, this equations, equation 6, so we can rewrite this and we can express this way. Okay. So, if dr by dt less than dg by dt, the point of tangency will disappear and the system will considered as a unstable because it moves upper steady state. So, at these conditions here, so systems will move from here to this upper steady state. So, this is the Runaway conditions. If this is means heat removal dRT by dt less than dg by dt, then systems would be Runaway conditions is there, and systems lower steady state to upper steady state it would move, means reactor temperatures. So, means if we start the reactions at lower steady state, this is lower steady state temperature and this is upper steady state temperature, or this is also, or you can say this is the upper steady state, this temperature is upper steady state. So, Runaway conditions should be there, and systems if sudden or any sudden slight increase in the pulse increase in the temperatures inside of the reactor, increase in the temperature, then systems move to the upper steady state. Okay. So, if heat exchange terms, here kappa is there, kappa you have noticed that is equals to UA by FA naught Cp naught. So, kappa you can put it here, we can put it here. So, if we can decrease the kappa, kappa how we can decrease? if UA decrease, this is kappa, kappa will decrease if UA decrease, okay. Kappa will decrease if UA decrease. UA what is? Overall heat transfer coefficient and area, heat transfer area, this is the product. So, if this product is decrease, then kappa will decrease. If kappa is decrease, then corresponding Tc, that value also will change, okay. And in that case, if heat exchange terms UA is decreased, kappa will decrease, and we will no longer have a point of tangency, and as a result CSTRs will run away to the upper steady state. So, upper steady state will reach, okay, at this particular conditions, okay. So, how we can avoid that, means Runaway conditions, how we can avoid, means we should operate the system. So, there is no Runaway conditions, means one steady state would be there and the steady state temperature would be such that there is no side product formations or other things are there, means evaporations, decompositions is not there of that reactants. So, how that we can do? So, this is the means equation 3 we have developed, equation 2 we have developed, means heat generations and gradient of heat removal, these terms we have developed. So, now Runaway conditions exist when dRT by dt less than dg by dt. So, it means this, then Runaway condition is exist. So, we have to find out the value kappa Cp naught, we have to multiply, we have to find out this value, and we know the activation energy T star R GT star. So, if we see that this value is greater than this, means if it is 0.5 and if it is 0.6, so then under these conditions Runaway exists. So, that we have to avoid, or if we see that or if it is less than 0.4, okay. These conditions means if we find out those value, if it is equal, left hand side right hand side coming equal, then it is okay. If right hand side this value is greater than this, so then also acceptable, means Runaway will not exist in the system. So, this is means whenever we design a reactor systems for a heat exchange is there, so we should avoid the Runaway conditions, means then to operate that reactors, okay. So, we should always follow this, okay. So, here Runaway exists and means let us say if we operate the reactor temperature here. So, if we plot Cp naught into 1 plus kappa, means these terms, and against Tc, if we plot this A star curves will come, this A star curves, A stars, what is A stars, that we will discussed. A star is this, okay. So, A star, that is the gradient of heat generation terms basically. So, if we are able to find this A stars against Tc, if we plot, so the lines would be like this. If our operating temperatures inside of the reactor, the steady state temperature is within these lines, means left these sides, then it is stable and Runaway does not exist if we operate the reactors. If we operate the reactor at these conditions, then unstable and Runaway exist, okay. So, always we should prefer the reactors should operate or work at this particular point or that particular steady state temperatures, okay. So, here you can see GT dGT by dt equals to A star. So, here A star against Tc we have plotted. So, if we means operate these stable steady state temperatures and then slightly increase the Tc temperature, so it would reach here and reach here. So, up to that we can go, and if we go beyond that, then unstable or unsteady state is there and Runaway conditions would there, okay. So, this way we can means at this particular point, means this sides there is no Runaway or multiple steady state is not there or higher steady state temperature does not exist, then so that way we can operate the reactors, okay. So, here at this particular points is good, means here these conditions will satisfy. Okay. So, therefore, we can operate the reactors at this particular means steady state temperatures. Okay. So, once it is satisfy these conditions or this. Okay. So, this way we can avoid the Runaway conditions. So, let us say suppose these are the things we know, means just I am writing to get an idea. Let us say if RT decreases means heat removal, means when we operating the reactors, heat removal means coolant circulation is there. If we decrease this component, so heat removal means coolant circulation rate if it suddenly drops, then heat RT term will decrease. Okay. If RT term is decrease means initially it was there, if heat removal terms is decrease, so then means Cp0 into 1 plus capacity, the stability decrease at constant Tc temperature, the stability decrease at these conditions, at this particular, if RT is decreased, the stability is decreased. Okay. If RT is fixed, heat removal is fixed, means this is fixed, the stability moves towards instability. If this is fixed, means heat removal terms is fixed and the stability moves towards unsteady by increasing Tc, temperature moving from this point to this and then this. So, Tc1 to Tc2 we are moving, and Tc can increase by increasing T0. Tc how we can change? By changing T0 or Ta, okay, for a specified kappa. So, if ambient or coolant temperatures or feed inlet temperature if we change, then Tc value will change. So, by that way we can change the means we can change, or Tc we can increase. Okay. By increasing this or this we can increase the Tc, by that way we can means from here to here it is moving. So, then unstable conditions it is moving. So, we cannot go beyond this. Okay. So, the temperatures if we move beyond that, then unsteady state means here stability is there, but here unstable or unsteady state or Runaway conditions is there. Okay. So, I think it is clear to you. So, means how or why we can avoid the Runaway conditions when we operated reactors, and always we should prefer the reactor should operate a steady state condition such a way that means the temperature would be such that it would not affect in the overall reactions. Okay. So, today what we have discussed, we have basically started with Runaway reactions in a CSTR, and when multiple reactions we have not discussed yet. So, that part will let us see in the next means series reactions, parallel reactions, that part we will discuss, and this chapter would be complete. So, Runaway conditions, how to avoid the Runaway conditions for a reactions or of a reactions when reactions is operating a steady state. So, if we operate reactions as a lower steady state, so then slight increase or decrease of the temperature, increased temperatures. So, heat generation should be more than heat removals, then the systems will reach to the upper steady state temperature. So, sometimes the upper steady state temperature is not good for the reactions. So, once it is not good for the reactions, so then how we can avoid that? So, for that heat removal terms we have to change such a way by changing or decreasing the overall heat transfer coefficient or heat transfer flow rate or somehow. So, then heat removal line moved to this way. So, then one steady state temperature we can get, and that steady state temperature should be such a way that that would not affect overall the reactions. Okay. So, means for the Runaway conditions, what is called Runaway conditions or ignition temperatures, means how we can get that from energy balance equations. We can get this means from the equation 2 we know dRT by dt and dZT by dt we have developed. So, equation 5 and once we know, and from there the critical temperature difference we know. So, that critical temperature should be such that, so Runaway conditions we can avoid. The difference between the reactor temperature and the feed temperature exits, the transitions to the upper steady state will occur, and then reactions will or reactors will operate at steady state temperature. So, that we have to look into that how we can operate the reactor at lower temperatures. Okay. As if we can get lower steady state temperature, low steady state temperature to operate the reactors. Okay. So, these conditions we have to avoid, and so always we have to prefer the conditions where to avoid the runaway conditions, these conditions we have to choose. Okay. So, dRT by dt means heat removal gradient should be greater than equals to the dGT by dt. Okay. So, based on that we can, once we design the reactors, we should keep in mind means to avoid the runaway conditions, to avoid these are the secondary reactions, evaporations of the materials or the reactants. Okay. So, today is up to this. So, I think it is clear to you. Thank you. So, today is up to this. Okay. Thank you.